Okay, Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3, going to do the presentation for the study on the economic load dispatch and unit commitment. So our group member consists of Iman Zul Hakim Isyahimi, and myself, which is Muhammad Ni Abdul Mahimi, and Tengku Muhammad Irfan bin Tengku Ilham. Okay, first of all, what is the economic load dispatch? Economic load dispatch is a process of deciding what's the individual power output should be of the scheduling generating unit at each time point. The economic load dispatch is important where to find the minimum cost of the power while operate the generator based on the requirement load. Economic load dispatch also important to maintain the system and generator reliability at the same time able to supply the load with the requirement power demand. The economic load dispatch is a bit different with the unit commitment, where the unit commitment use the turn on and turn off of a generator. Meanwhile, the economic load dispatch decide on how much the electric need to be powered, generated by the generator. And then we're going to continue with the description of the question. So it's content of three different unity unit, which is A, B, and C, where they run on the different energy source, which is the thermal coal, natural gas, and diesel, where the operating the power minimum for each generating is different, and also the power maximum also different. And then from this study, we need to solve by using lambda iteration method of the power demand, which 500 megawatt, 800, 900, 1000, and 1200. And then we need to determine the optimal dispatch of all unit to meet the load demand for each cases. And then the study also need to perform the result in graph to show the relationship between optimal dispatch costing and the incremental cost. Then Iman will continue with the follow chart.
Okay, thank you, Anik. So now I will explain about the flowchart. So this is our flowchart for this mini project. So first, the program will with start, and we need to read and determine the term of A, B, C, D, power demand, Pmin, and also Pmax. So actually, the A, B, C are the value that we take from the equation at input-output characteristic. For term of D actually is the value of cost thermal generating. So for the Pmin actually is the minimum output limit, and for the Pmax is the maximum output limit. So the power demand actually the value that we get is at the equation. The power demand that given is 500, 800, 900, 1000, and 1200 megawatt. So after that, we need to choose the initial lambda. So for this our mini project, we have choose 3.3 as a lambda value, as the initial lambda value. So after that, we need to set the iteration starting with 1, since we need to use the lambda iteration for our mini project. So after that, we need to calculate the PKI. So actually the PKI is the value of PK1, PK2, and also PK3. So after that, we will get the three possibilities. So the first possibilities is if P min is below equal PKI and the PKI is below equal Pmax. So actually, if the statement is true or yes, so actually the value is set to PKI, which means the value is set to PK1, PK2, and also PK3. But if the statement is false or no, the the statement will go to the second possibilities. So the second possibilities is PKI is below or below equal Pmin. So if the statement is true or yes, it will go the statement PKI is equal to Pmin. But if the statement is false or no, it will go to the third possibilities. So the third possibilities is PKI um larger equal Pmax. So if the statement is true, so the PKI is set the value of Pmax. But if the statement is false or no, it will will calculate the PK total. So PK total means the sum of PK1, PK2, and also PK3. So after that, we need to calculate the delta P. So the delta P is the formula that we used for the delta P is power demand minus with PK total. So we can get the delta P. So after that, we can calculate the error delta P by using the value of PK total divided with power demand. So we have two possibilities. If the mm, if the value is negative 0.001, below than delta P and below than 0. So if the statement is true, we will display the result of iteration, the final iteration of PK, delta P, error of delta P, lambda, lambda output generator, and also the cost for and also the cost for the final result, and the program will end. But if the statement is false or no, actually it will go to the second possibilities. So the second possibilities is if the value is if the value negative 0.001 is below than delta P. So if the statement is false, so it will go to the um, new delta equals to old delta plus with delta lambda. But if the statement is yes, so the new lambda will equals to old lambda plus with delta lambda. So actually the statement will go to the second iteration, and it will calculate the peak. It will repeat the same step after they get the final result of iteration of PK, delta P, error of delta P, lambda, output generator, and also the cost. Actually, the value of negative 0.001 is the tolerance 0.001. So next, we're going to move to the coding for our project. So now we're going to move to the so actually we have two type of coding. So the first coding is power demand for 500 megawatt, and the second coding is for 800, 900, 1000, and 1200 megawatt. So for the 500 megawatt, we have used the different coding because it have the load sharing. So this is the coding for the power demand at 500 megawatt. So we can see at the line 1 to 25. So is the description. Actually, this is the description for the that we have get from the question. So the power demand we have set for 500, lambda we have set for 3.3, and the A1, B1, and C1 actually we have get just as I say just now is from the input and output characteristic. Same with the A2, B2, C2, A3, B3, C3. So this is the P min and P max 1, 2, and 3 that we have get from the our mini project question. So the PLs we have set for 0 because they have because it no for this our mini project we have no losses. So that's why we have set to 0. So at the line 23 to 25, this is the first iteration. So we have used P11 equals to lambda, lambda minus with B, divide with 2, multiply with A plus lambda, multiply with P losses. So actually, as we can see at the second picture, is the continuous of the first iteration. So actually, we have to do the same method for the P21 and P23. So next, we have set the limit generator. So the limit generator, as we can see, if this is the statement for the limit generator. So we can see that if the P min 1 is below, then is below equal P11, and P11 equals below equals P max. So if we choose P11, as if we choose P11 to equals with P max. So after that, we can see the P min 2 below than P21 and P21 below equal to P max. So it will choose P21, else P21 equals to P max. So the same things have been done for the third possibilities. So next, for the line 51 to 75, so is the value the equation for the delta P. So this is the formula to calculate the delta P, and for the line 54 to 61 is the equation for dp per d lambda. So at the line 63 to 65 is the value for to find the value of delta lambda. So at the line 67, it show that we have make the second iteration for the our mini project at the 500 megawatt power demand. So we can see that for the next picture, the same concept we have used to get the value for the second iteration. So this is the picture for at the figure 2.6. This is the third iteration, and we will go to the fourth iteration. So at the fourth iteration, actually we will actually at the fourth iteration, actually you can see, as we can see at the limit generator, we have set if the P min 1 is below equal to P14 and P14 below equal to P max 1, so it will choose P14. So as P14 as P14 plus P max P max 3. Why we have write P14 plus with P max 3? Because of the value of P11 is below than the limit of the generator. Because as we can see at the question, the minimum output limit at the P1 or P14 is around 200. So because it has a below value, so we need to plus with P max 3. And we can see if the P min 2 is below or equals to P24 and P24 is below equals to P max, so it will choose actually it will choose P24, but we have write the equation Pn equals to P24 minus with P min 2, because of we need to supply the power to the P3, because as we can see after the P3 4 supply the value to the P14, actually the value of the value power of P34 actually will become um lower than minimum limit. So that's why we need to take the we need to supply the power from the P24 to P23. So as we can see at the uh third statement, it show that if P min 3 below than below equals P34 and P34 is equals P34 equal below equals P max 3, so we choose P34. Else the P34 equals to Pn that come from the P24 plus with P34 minus with P max 3. So next. So the same concept that we have used to find the delta P, dP per d lambda. And last, we have at the last coding, yes, we have find the total cost. So actually, the first at the line 203, it showed that the total gen power that we have used for the 500 megawatt power demand. And as we can see at the 200 and line 270, it showed that the total cost for the generator that we have used. So all the answer actually has been displayed at the power had been displayed at common at the MATLAB, and the result will be explained with my partner later. So now we're gonna move to the next coding. for the second coding, which that used for 800, 900, 1000, and 1200 megawatt power demand. So actually, this is the coding for the second method. So actually, we have used, yes, we have used the power demand that we have given from the question. The A, B, and C that we have get from the input output characteristic, Pmin and Pmax. P losses we have used 0 because they have no losses. The initial lambda. So this is the iteration. So the iteration, we need to set we need to set to get the minimum value of um, delta P, and the error of delta P that we get is equals to 1. So at the line 70 is the about the continuous decoding for the continuous iteration. And for the at line 19 actually is the formula to find the PK1, PK2, and also PK3. It's a little bit different with the coding at the first coding, but the answer that we get actually is same. So at line 20 is the PK total, which is PK1 plus PK2 plus PK3. Next, the coding is show about the generator limit. So generator limit, you have three possibility as I say just now. So next, the power limit, the power losses. So we don't have power losses, so we have set it to 0. Next, to find the delta P. This is the formula for delta P. The value of delta P, actually, we have choose the last iteration. After we get the value of delta P, is below than, is below than negative 0.001 or tolerance 0.001. So next. So this is the coding for the dp divide with the lambda and delta lambda. So the last at the line 97 is the formula to find the output generator and also the cost. So actually the cost, as I say just now, all the result have been shown at the common window, and it will tell with my friend later. So at the line 84, this is the next iteration. So the coding will continue to make a next iteration until finish. So now I will pass to Tengku Muhammad Irfan to tell about the result and also about the discussion.
Thank you, Muhammad Iman. Thank you, Muhammad Iman. And for the result, for the table 3.1, the result is of the power generator before it set to minimum and maximum limit, which is uh, the P1 will get all the same as P2 and P3. And for the table 3.2, the result of the initial generator after we set the minimum and maximum limit. Next. For the table 3.3, the result optimal dispatch after using the lambda iteration. Lambda iteration will the number of iteration depend on the error of the delta P, which is 0.001. For the 500 megawatt, the number of iteration is 4 because uh, the delta P will get lower than 0.01, and the iteration will be stopped because if the iteration will goes on to 5 6 iteration, the answer will get the same as the iteration at the number 4. And then for the 800 megawatt, 900 megawatt, and 1000 megawatt, and also 1200 megawatt, the iteration is the same, but the number of iteration will get higher, because if the power demand is higher, the number of iteration will get higher. And the delta P, to get the delta P, we uh we will minus the PD with the P1, P2 and the P3 power generated. And then next slide. At this, for the table 3.4, the result of the sum of power optimal and power demands. And this at the the right side is the graph of the optimal dispatch, which sum of power with the lambda. And the at the 500, the P2 will get minimum power, because to support the P1 and P3 power, P2 has to activate at the minimum power to get the 500 power. And for the 800, the P3 will generate at the full power, which is 200 and 240. And for the 900 also, the P3 will generate the power for the power generated at the full power too. And for the 1000 and 1200, the P2 and generating unit of P2 and P3 will activate at the full power too, because to support the power of 1000 megawatt power demand, P1 will activate at a certain level, which to support the 1000 and 1200 megawatt. And next slide. This is the for the table 3.5. The result of this is the result for the cost and incremental cost. As you can see, the highest of the cost is 1200 megawatt. And the this for the total cost, this is the minimum cost that we will get after we generate the power for the generating unit. And then I will pass to Muhammad Anik. Thank you.
Thank you, Irfan. I'm going to continue with the conclusion for this study of the economic load dispatch and the unit commitment. So the economic load dispatch is used to achieve the generated power equal to load demand with the minimum cost. So, and then the economic load dispatch is the most efficient way and effective way to find the generated output of a generator within the limit, so that the safety of the generator, we can keep up the safety of the generator, and the source price can be minimized, where the cost can be minimized also. And then the cost of the source become cheaper as we applying the uh, economic load dispatch, as the unit commitment, sorry, the cost of applying the economic load dispatch are less cheaper than the applying the unit commitment, where the economic load dispatch can share and schedule the required power, but according to the power limit or the power load that been required. And then As the power demand increase, the incremental cost to operate the generator also increase, although the lambda are the same. Okay, that's all for us. Thank you.
Thank you.